Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'll be talking a little bit about clustering and neighborhood graphs. Okay. And so let me start with the clustering part. Okay, so what is clustering? You're given a bunch of points and you want to divide them into groups. Okay, and now this is something that arises in sort of two rather different contexts. Okay, the first of them is vector quantization, which is integral to, say, audio and video coding. So over here, the data points are typically samples from some vast underlying space, typically a continuous space. Okay? For example, each data point might be a small sound snippet from the space of all possible speech samples. Okay? And the goal in these cases is to find a small set of representatives, a small finite set of representatives for this really large underlying space. Okay? In audio coding, for example, you want to find a small set of representative signals, and subsequently, every sound will be approximated by its closest representative. Okay? In such cases, it's completely irrelevant whether there are any natural clusters in the data. Nobody cares. All you want is to get good coverage of this space. Okay? You want to find a bunch of centers that cover the space nicely. Okay? So I'll be talking about sort of a different way in which clustering is used, and perhaps a more common way in which it's used, where the goal is to find meaningful structures in the data. Okay? So sort of natural groups that exist in the data. And just to give you another example from this domain of sound signals and so on, when a baby is first born and is day one, it's it hears all these utterances from its mother and father and so on. And initially, these utterances basically form a continuum. But by the time the baby is 6 to 9 months old, it has clustered these sounds, which were initially a continuum, into the phonetic categories of its mother tongue. And these are natural clusters in the sound space, 40 to 50 clusters, okay, 40 to 50 phonemes. Okay. So that's the kind of clustering that I'll be talking about, finding natural groups in data. And this arises all the time in applications. For example, if you have a new data set and you want to do exploratory analysis of it, one very useful thing is to see if there are natural groups in it. Or if you have a company and you want to find natural cohesive groups of customers for things like targeted advertising. Or you have a data set and you want to get a clustering of it that you are going to use subsequently for semi-supervised learning or active learning. Okay. Anyway, so there are all these sort of endless situations in which it's used, and so let's just look at this picture. So we want to find the natural clusters in the data. What are they? Like how many are there? Are there 2 clusters? It could be. You could have one here and one there, or are there 3? Like maybe there could be 3, or maybe more. It's hard to tell, right? It's hard to tell what the right number of clusters are. And in fact, there are these various criteria that will give you a number. So there's minimum description length and Bayesian information criterion. And they'll tell you, well, there are 3 clusters over here or something like that. But one look at this picture should convince you that you should be really skeptical about such measures, okay? There's obviously no right answer, okay? And so what we'll be doing is we'll just be looking at hierarchical clustering. Okay? So the nice thing about a hierarchy is that it contains all levels of granularity. Okay? So at the top level, you have all the points. If you want 2 clusters, you have that. If you want 3 clusters, you have that. If you want 4, you have that, and so on. So we'll look at a case where you build an entire hierarchy over the points. Okay? Now, this might seem more difficult than flat clustering because in order to build a hierarchy, it seems like you have to do a flat clustering at every possible granularity, and then somehow massage all these clusterings together into a coherent tree. Okay? But actually, in many ways, hierarchical clustering can be easier because it avoids making some choices that are difficult or almost impossible to make. Choices like what is the right number of clusters. Okay? And so that's something that keeps popping up again and again in a lot of unsupervised learning, that when you move to sort of a hierarchical view of things, you often end up avoiding a lot of difficult choices. Okay? Okay. So we're going to be doing hierarchical clustering. Okay? So, as you know, there's lots of clustering algorithms out there, k-means, EM, et cetera, et cetera. Okay? One algorithm for hierarchical clustering that's pretty well known is the single linkage algorithm. Okay? And one of the remarkable things about this algorithm is that it's used in both statistics and computer science communities for completely different things. The statisticians call it single linkage and use it for hierarchical clustering. The computer scientists call it Kruskal's algorithm and use it to find the minimum spanning tree of a network. Okay, so it's exactly the same procedure used for two rather different tasks. Okay, and so let's look at what this procedure is. Okay, so this is due to Kruskal, who passed away a few years ago. Okay, so this is the way it works. This is the way this hierarchical clustering algorithm works. Many of you are probably familiar with it, but let's go through a quick example. So over here you have 10 points. Okay, you start by merging the two closest of them. Okay, and so now you have one cluster with 2 points in it. Then you merge the next pair. So now you have two clusters each with 2 points. Then you merge the next pair. And now the next closest pair of points is this point and this point. So you end up getting a cluster containing 3 points. Okay? And you proceed in this way. And then you have a hierarchy. Okay? So at the top level, you have all the points. If you want to get 2 clusters, you just cut the longest edge, and you get 2 clusters. If you want to get 3 clusters, you cut the next longest edge, and you get 3 clusters, and so on. Okay, and you can get as many clusters as you like. So it's a nice, simple algorithm. And so the question is it any good? Is it a good algorithm? And that's something that has been a little bit difficult in clustering in general. There's a whole slew of clustering algorithms out there, and it can be hard to tell which ones are better than others. Okay? So because of this, there's been a whole slew of theory work where, what has happened is that people write down some properties that they think good clustering algorithms should possess. And then they analyze clustering algorithms to see which of these properties they actually possess. So this is actually an enterprise that started a long time ago in the 1970s. Mathematical biologists who build these phylogenetic trees, they started with this whole axiom or property-based analysis of clustering. And in 2001, John Kleinberg resuscitated this. So Kleinberg came up with 3 axioms, or 3 properties that every clustering algorithm should have. And he found that actually there is no clustering algorithm that has all 3 properties. But the one that comes closest is single linkage. And now after that, people came up with other sets of properties. And yet, again and again, single linkage seems to keep cropping up as, a really good algorithm. But in practice, it's deeply flawed. Okay? It runs into a lot of problems. And so, the issue is, what is wrong with all of this? What is wrong in all of these theoretical models? Why do they keep suggesting single linkage as being, the right way to hierarchically cluster? And what is wrong with them, basically, is that they completely ignore the statistical aspect of the problem. And as soon as you view clustering statistically, you see what's wrong with this algorithm. Okay, and so let me explain what I mean. Okay, so when you're clustering n data points, these are not n arbitrary points that have materialized out of nowhere. Rather, they are n draws from some underlying distribution, from some unknown underlying distribution. For example, the distribution of utterances from a mother to her child. Okay, so there's some distribution. We don't know what the distribution is, but the points have come from that distribution, and the mere fact that they have been generated in this way gives them special properties. Okay? So in particular, one thing we would hope is that if we got two samples of points, two random samples from the same distribution, and we clustered both of them, they would each yield similar clusterings of the underlying space. Okay, so that's one property that we'd want, at least if the number of clusters were large. Okay, and further along that line, as you get more and more points, you would hope that this clustering you have eventually converges to some underlying clustering, to some clustering of the underlying space. Okay, and that's the property that we would call consistency. Okay, that as the number of points grows, these clusterings that you get, the clustering with n points, n plus 1 points, and so on, these clusterings actually converge to something. They converge to some partition of the space. Okay? So that we would call consistency. And we'd also hope that this thing that they're converging to is something meaningful. Okay? That's something that really tells us something about the underlying density from which the points have come. Okay? Now, if you work in classification, then all this talk about consistency will seem really obvious and naive. And the reason for that is that in classification, we have a very well-developed theory of consistency, okay, using large deviation bounds and the VC dimension and all that kind of stuff. But in clustering, the situation is much more primitive, okay? And consistency has proved to be rather elusive, okay? So just as an example, like if we take the k-means algorithm, this is probably the most popular clustering algorithm in the world, okay, k-means. So suppose you were to run k-means on n, you're getting points from some underlying distribution, you run it on n points, then you run it on n plus 1 points, then you run on n plus 2 points. Do you converge to something? You know, does the clustering converge? It turns out that the only thing that's known is that the answer is yes. If your clustering algorithm always finds the global optimum of the k-means cost function. Now that's a tall order, because optimizing the k-means cost function is an NP-hard problem, even for just k equals 2, even for 2 clusters. Okay? But even supposing you were able to do this, the thing that it converges to is simply the k-means clustering of the underlying density of the, okay? And it's not at all clear that that's meaningful or interesting. Okay? So basically, the statistical theory of clustering is pretty dismal all in all. And with that backdrop, single linkage is actually not too bad. It is trying to converge to something. And the thing that it's trying to converge to is something actually very sensible. And so let me tell you what it is. Let me tell you what it's trying to do. What is it trying to converge to? So here is an example of a density, okay? And so it's the sort of density from which you might be drawing points. I think most people who looked at this density would agree that there seem to be 4 clusters over here, okay? There are these 4 humps over here. And the only thing that's unclear is where exactly we draw the boundary. Like, is this a cluster or is that a cluster, okay? You know, well, the good thing is that, you know, since we're talking hierarchically, we don't have to make any of these choices, okay? This is a cluster, and so is this, and so is this. They're all clusters, okay? And so we can just define clusters in a very simple way, okay? We say, pick any lambda, pick any density level lambda, and look at the region where the density is more than lambda, okay? So you're going to get a few connected components. Any of those connected components are bona fide clusters. That's a valid cluster, okay? So you've got some density, you cut off the density at some point, and you get a bunch of connected components. That's a bona fide cluster. You pick a different density level, you get other clusters. So there you get a whole infinitude of clusters, but they form a hierarchy. And we call this hierarchy the cluster tree. And that is what single linkage is trying to converge to. It's trying to converge to this cluster tree, okay? So this is just, it's just the usual, you know, path connectedness, you know, that there is a path from one to the other. So you have this region where, let's say the density is continuous. So you have a region and, you know, it's just, are they connected? Is there a path from one to the other? Okay, so just by way of example, let's say we have this one-dimensional density. Okay, so we can pick any density level. Let's say we pick level lambda 1. At that level, there is just one cluster. This is the cluster right there. Okay? We can pick a different density level, lambda 2. At that level, there are two clusters. This cluster of points, this connected component of points with density more than lambda 2, and this connected component with density more than lambda 2. At lambda 3, there are also two clusters, and so on. Okay? And so there are infinitely many density levels, and so there are infinitely many clusters, but they form a hierarchy. Okay? If you look at any two clusters, they're either disjoint or one is nested inside the other. So that means that they form a tree. And so we get this infinite tree called a cluster tree. So I said that single linkage is trying to converge to this thing. Okay, so what does that mean? And like, in what sense is it trying to converge? So let's say we draw a sample from this distribution, and let's see what single linkage is going to do on that sample. Okay, so it's going to start by merging the two closest points. Okay, so it'll merge 2 and 3. And we can think of that, we can think of this cluster as being a finite approximation to that cluster right there. Okay? Then it merges in the 1. And we can think of this as a finite approximation to this cluster. Okay? Or we can think of this subtree as a finite approximation to this cluster. Then it merges those. And we can think of this subtree as a finite approximation of this cluster right here. Then it merges in a 4. And we can think of this subtree as a finite approximation to this cluster, and so on. Okay? And so it really does seem like the tree that single linkage is producing is somehow consistent with the cluster tree. Okay, just sort of anecdotally. But we have to say precisely what we mean by consistency. And Hartigan came up with, in the 70s, came up with a very sensible definition. Okay? And, you know, it's kind of, there's a lot of math over there. But let me just tell you what the definition says, okay? I just tell you in words, okay? So this is what consistency means. What does it mean for a hierarchical clustering algorithm to be consistent? Well, what it means is that take any density level, like let's say we take this level, and look at any two clusters, like let's say this cluster and that cluster, okay? So look at two of these clusters. Now you have a finite number of points, and you're going to hierarchically cluster them. What you want is that the points that fall in this region and the points that fall in that region end up in disjoint subtrees. That's what you want, okay? So the points that fall in this region, there'll be, in this case, 4 of them, and the points that fall in that region end up in disjoint subtrees, and indeed they do. This is one subtree, and that's another subtree. Okay? So that's what consistency means for hierarchical clustering. That's Hartigan's notions of consistency. Okay? And we can see that in this case, the single linkage algorithm really is consistent. And this is just with 6 points. As far as the definition goes, we just need this to hold as the number of points goes to infinity. Okay? Now, it turns out that this example is not just a coincidence. Okay? Hartigan showed in 1975 that single linkage is in fact consistent in one dimension. Okay? So no matter what the underlying distribution is, there is some infinite cluster tree associated with that distribution. And when you run single linkage on larger and larger data sets, you will converge to the cluster tree. This is one of the few nice results in the statistical theory of clustering. Okay? So we have this algorithm, single linkage, that is actually converging. And what's more, it's converging to something that's meaningful and sensible. Okay, so this was a really nice result in clustering. And so the next natural question is what happens when the dimension is more than 1? Okay, and unfortunately the news becomes very bad immediately. Okay, so 7 years later, Hartigan, the same guy, showed that even when the dimension becomes 2, okay, single linkage stops being consistent. Okay, and he did this via a reduction to continuum percolation, which and I'm going to talk a little bit more about percolation later on. Okay, so it's a very beautiful argument, but basically the problem is the following. Okay, so let's say you have 2 high density regions, these like this and this. These are clusters, basically, right? What we want single linkage to do is to connect all points in this region and to connect all points in this region before it creates any links between the 2 regions. Okay, that's what we want from consistency. But that's actually a tall order when the dimension grows more than 1, because it's really easy to have a point close to the boundary here and a nearby point close to the boundary there, and just have that bridge created before this side has been fully connected, or before the other side has been fully connected. It doesn't happen in one dimension, but as soon as the dimension exceeds 1, it happens inevitably, okay? And so single linkage stops being consistent. And so at that point, Hartigan, posed this open problem: find a way to do consistent hierarchical clustering in higher dimension. And that's something that we figured out a few years ago, 4 or 5 years ago, and since then there's been a lot more work along that line, and so that's what I'll be talking about today, okay? So we found that, in fact, you can do hierarchical clustering. You can actually converge to the cluster tree. And the algorithm that you use to do that is just a very small variant of single linkage. It's almost the exact same thing. You just have to tweak it a very little bit. And to see how you need to tweak it, you just need to look at it in a different way. You need to think of single linkage in terms of neighborhood graphs. Okay, and so I'll talk about that. Yeah?
No, I think it's an illusion, because the same issue can happen even in the one-dimensional case.
Right. So all that happens is that it's much more likely in 2 dimensions. It's much easier for it to happen. It's because in 1 dimension, these boundaries between clusters are tiny, whereas in 2 dimensions, they suddenly become much larger, right? And so and as n goes to infinity, the probability of one goes to 0 and the probability of the other goes to 1. Okay? Right. So let's talk about neighborhood graphs. Okay, and so these are really popular in machine learning. A neighborhood graph is just a way of capturing the sort of local geometry of a data set. Okay, so you want to capture the local structure of data. So the way you do that is you create a graph with a node for each data point, and you put an edge between points that are close by. And so you start with this data set that is high dimensional and chaotic and hard to understand, and you end up with this really nice, clean mathematical object, okay? And then that's the starting point for what you want to do next, okay? So if you want to cluster, you can look for small cuts in this graph. If you want to do semi-supervised learning, you label a few points in this graph, and then you propagate labels along edges. If you want to do manifold learning, you find an embedding of the points that respects the neighborhood structure shown in this graph, and so on and so forth, okay? So these are very popular objects. You take this complicated data set and you make it into this really nice graph, okay? So that sounds very good. And so the question is, how exactly do you build this graph? Like, how do you decide where to put the edges? And it turns out that there are 2 popular ways to do it. Yeah?
How is that used for regularization?
Oh, regularization. Yeah, so, so for example, if you're trying to learn a function over the space, what you want is the function should have similar values at neighboring points. Okay, so if you're learning you just want to learn some arbitrary function, okay, like non-parametric regression, you can regularize it by asking that the function's value at this point and the function's value at that point are very close together. Okay, so that's an example. Okay. So here are 2 popular ways. There are basically 2 popular ways of constructing these graphs. And the reason that there are 2 of them is that neither one is entirely satisfactory. Okay, so it's just a question of finding the lesser of the 2 evils for the task at hand. Okay, now the first way is to join any 2 points whose distance is less than some threshold r. Those are the points you connect. The second way is to join 2 points if there are k nearest neighbors of each other. Okay. So these are the 2 ways, and let's see what their shortcomings are. Okay, so the problem with the first method is that often you have clusters at many different scales. Okay, so you can have a situation like this where there are 3 clusters at different scales. Okay, so let's see what happens. Suppose you set R to be something small. Well, then you'll get edges inside here, but you might get no edges at all inside this big cluster. On the other hand, if you set R to be larger, you'd get edges in here, but you might end up merging these 2 clusters. Okay, so you just end up in trouble either way. Now, this kind of multiscale structure is not pathological. It is the norm. Okay, so if you, for example, think of the MNIST data set of handwritten digits, so you have a cluster of zeros, a cluster of ones, and if you actually look at the radii of those clusters, they're all very different. The cluster of ones, for example, there's not much variation in the way people write ones. So that's a really small cluster. That looks like this, whereas something like the eights looks like that. So multiscale structure is the norm. We have to deal with it. Okay. Now, this other scheme where you connect each point to its k nearest neighbors, the hope is that those nearest neighbors are going to be in the same cluster. Okay? And I think it would do okay on this data set. It would probably do fine here. But then you run into another problem. Okay? In large data sets, it's very common to have points that are outliers, or at any rate are outside the central region of each cluster. The minute you have something like this, you could have these spurious connections where this point, which is a bit of an outlier, ends up being connected to both this and to that, and then later wreaks havoc with whatever it is that you're trying to do. Okay? So anyway, so both these methods have their problems, and of course there's the additional problem of having to figure out exactly what R and K you should use. Okay? But the high-level issue over here is that the high-level problem is that you're trying to take something that's multi-scale and represented it in a flat graph, okay? And that's just inherently difficult, okay? So what's a way around it? Well, instead of just creating one flat graph, how about creating a hierarchy of nested graphs? Okay, that should get around this problem. And in fact, that's exactly what single linkage implicitly does, okay? And so let's look at single linkage in that way. So here's the single linkage algorithm. Another way to think about single linkage is that it's got this knob that starts at 0, and the algorithm slowly turns the knob until it reaches infinity. This knob is the scale, okay? And let's call it R, okay? So when the knob reaches R, what you do is you join together any points that are a distance R or less from each other. Okay, you join together those points and you output the connected components that you find. Okay, and any singleton components you just ignore. Okay, and then when the knob goes a little higher, then you throw in some more edges and then you output those connected components and so on. Okay, so single linkage really is implicitly creating this hierarchy of neighborhood graphs. Okay, now another way to sort of think about it is that as this knob is being turned, initially none of the points are active. Okay? The only time a point xi becomes active is when the knob reaches R of xi, which is the distance from xi to its nearest neighbor. When the knob reaches that value, all of a sudden xi is activated. And thereafter, xi is always going to be in the graph. Okay? So each node becomes activated at some point. Thereafter, it's always in there. Okay. Now, and so this is a nice algorithm, but we saw that it's not consistent. So what do you need to do to it to make it consistent? And it turns out that you need to change almost nothing. Okay. So let me show you the amended version. Okay. So this is regular single linkage, and this is the amended version. I've literally just included 4 more letters. Okay. So what are the changes? Okay. So the first change you make is that I said you were turning this knob, and a point xi becomes active when the scale reaches R of xi, the distance from xi to its nearest neighbor. What you do now is you look at the distance from xi to its kth nearest neighbor. Okay? This just makes everything more robust, and we'll see why in a second. Okay, so each point gets activated a little bit later. Okay? Instead of when the knob reaches the distance to its nearest neighbor, you wait till the knob reaches the distance to its kth nearest neighbor. Okay? The other thing is when the knob is at R, you link up all points at distance less than R, but you also link up a few more points. You also link up points whose distance is less than alpha R, and alpha here is square root 2. Okay? And if you make these changes, then this is consistent in any dimension. Okay? So this is a slight modification of the algorithm, and it becomes consistent. Okay. Now, Now, consistency is an asymptotic property. Okay, it tells you what happens as the number of points goes to infinity. Okay, and now, of course, in reality, so we're only working with finite data sets, and therefore, we really care about what happens for a finite number of points, okay? Not just as the number of points goes to infinity. We want to know what happens when you have n data points, what kind of tree does it return then, okay? What clusters does it discover then, okay? So what we know is as the number of points goes to infinity, all the underlying clusters will be found, okay? Everything is going to be found as n goes to infinity. But what we might expect is that if there are some clusters that are particularly prominent, okay, or if there's some clusters that are salient, then they would be found pretty early on, even with very few points, okay? And so all we need now is a notion of cluster salience. And using that, we'll be able to get sort of finite sample results, okay? So, so what we need to do is to define how prominent a cluster is. So there's some cluster in the underlying density. In the previous, early on, we saw those 4 humps. In general, they're not going to be that salient, okay? But we want a notion of how salient a cluster is. And this might seem like a complicated thing, but actually it's very simple to characterize. There are just 2 effects that we need to take into account, okay? So let me tell you what they are. This is the first effect. Okay, so this is a cluster, and it's got high density throughout, okay? So this is a high density region. But it's got 2 sides that are connected by a narrow bridge. And so what will happen is that in a finite sample, if you have a small sample, it will probably just look like 2 separate clusters. Okay? So this is an example of a high density cluster that is hard to discover in a finite sample. Okay? And to deal with this, we will also talk about a buffer zone around each cluster. Okay? So for any set Z, like this cluster over here, and any number sigma, like 0.1, Z sub sigma is this, plus a buffer zone of size 0.1 around it. Okay? So we'll use that definition. So that's effect number 1. And the second effect is this. So here we have 2 bimodal distributions. They both have 2 clusters. But in this case, the dip between the 2 is much more pronounced than in this case. So these 2 clusters it should require much less data to discover that there are 2 clusters here than in that situation. Okay? So these are, simple observations. And it turns out these are the only 2 effects that one needs to account for. Okay? And so we'll define a notion now of how separated clusters are. Okay? So I'll say 2 clusters are sigma epsilon separated. So here are 2 clusters. Okay, now we're not making any assumptions about the density, so the clusters could be weird looking, and that's why I've drawn this kind of strange looking thing over here. Okay, so you take any 2 clusters, and we say that they're sigma epsilon separated if first of all they're separated, so there's some set S that separates them. And what I mean by separation is that any path from A to A prime has to go through S. Okay, so that's the separator set. Okay. But moreover, the density along the separator is less than the density in A and A prime. So the separator is in a lower density region, even if you put a buffer zone around everything. Okay? Even if you put a buffer of sigma around everything, you have this gap in density. Okay? So the main thing to notice over here is that no matter what the clusters are, they are separated for some sufficiently small sigma and epsilon. Okay, you look at any 2 clusters, there will be some, if you make sigma and epsilon small enough, they will be separated. Okay, but if you have 2 clusters for which the separation is larger, for which sigma and epsilon are larger, then you will discover them with just a very small sample. Okay. And so this is the result over here that one can show. And so here's what you can say, that modified single linkage procedure I told you about has the following property, and this holds uniformly for any 2 clusters, A and A prime. If you have 2 clusters that are this much separated, and their minimum density is lambda, then after the number of points exceeds this, the 2 clusters will be separated. In other words, they will show up in distinct subtrees of the hierarchy. Okay? So we know that as n goes to infinity, they are going to be separated. But the question is, how large does n have to be before these two clusters will appear in distinct subtrees of the hierarchy? And that's how large n has to be. And you can also show that that is as good as it gets, okay? And I'll say something about that later, okay? And so one way to think about it is that at that value of n, the hierarchy has these two clusters in distinct subtrees. The other way to think about it is that the algorithm is spitting out all these nearest neighbor graphs. And so there'll be some scale r at which the graph has the following property. A is within one connected component of the graph. A prime is within a different connected component of the graph. Okay, so that's another way to characterize that. And so why does this hold? And this is an exercise in continuum percolation. And so I'll just talk a little bit about this. Okay, so I'll just talk a little bit about connectivity in random graphs. Yeah. Is there any link between them? No, they could all. They are sort of separate numbers. They capture two separate things. They're just going to be small positive numbers. Let's just look at the definition. So sigma is the width of this buffer zone. And epsilon is how much smaller the density is here than here. Okay, so let's say the density over here is 100, and the density in the separator zone is 50. Okay, then epsilon is a half, because it's half the density. Yeah?
A few slides back you had mentioned that the k global optimum is, to find that is hard.
Mm-hmm.
And now it seems to suggest a method which is going towards the global optimum. So what do you think?
So the k-means global optimum, however, is a different clustering. So it's not, the k-means is not attempting to find the cluster tree. K-means actually is attempting to solve a problem that's more in line with vector quantization. Okay? So it's got a particular cost function where it's minimizing the squared distance from each point to its closest representative. And that particular cost function happens to be NP hard to solve optimally.
But if there was an underlying distribution on this k-means work, it's probably conceivable that actual clustering based on the underlying thing is what k-means will converge.
Unfortunately not. Yeah. K-means is actually much more suitable in the vector quantization context than in the other context of finding meaningful structure. Yeah, even though it gets used in both cases. Yeah, any other questions? Okay, so let me talk a little bit about connectivity in random graphs. So I think most of you are probably familiar with Erdős-Renyi random graphs, because these are the kind of random graphs we usually encounter in combinatorics and computer science, okay? So in these random graphs, you have n nodes. So you start by plonking down n nodes. And for each pair of nodes, you flip a coin, and with probability p, you put an edge between those two nodes, okay? So the randomness lies in the edges. There are n choose 2 random choices. You flip n choose 2 coins independently with bias p, okay? And you get this random graph. And the sort of question that one asks about these graphs is how large, for example, does p have to be in order for the resulting graph to be connected, or to have a component that's very large. Okay, these are the kind of questions that we would call percolation. Okay? Now, that's very interesting, but in statistics, the kind of graphs that we come up with are usually not of this kind, but rather they are random geometric graphs. Okay? So what a random geometric graph is that is the following. We have some unknown density, and we generate n points at random from that density. And then we put an edge between 2 points if they satisfy some criterion, like they're distance less than 1 apart, or something like that. So that's a random geometric graph. Okay? It's also a random graph, but it's very different in flavor. The randomness is not in the edges. The randomness is entirely in the nodes themselves. Okay? The points have been picked at random. So the amount of randomness is actually order n versus order n squared. So it's a different kind of random graph. It's been studied significantly less, but the kinds of questions one is interested in are exactly the same kinds of questions, like at what point do these graphs become connected and so on. And so these are the kind of random graphs that we will be dealing with. Okay, so when you're generating points from an underlying distribution, you inevitably end up with a random geometric graph rather than an Erdős-Renyi graph. Okay. So so let's go back to the algorithm. And so what single linkage is trying to do, or what any of these algorithms are trying to do, is that initially they're focusing on the high density regions. Okay, so single linkage. The first thing single linkage does is to take the two closest points and merge them together. Okay, and it's hoping that this is the highest density region of the underlying density. Okay, and that's it's reasonable to see why it's hoping that. But the problem is that the problem is sampling error. It's possible that just by chance the two closest points might end up being in a part of the density that's actually far from the highest region. Okay, such things can happen, and one mistake of that kind will completely derail the algorithm. Okay, so we need to make it a little bit more robust. And that's why instead of the distance to the nearest neighbor, we look at the distance to the kth nearest neighbor. Okay, so to understand this, it's useful to look at large deviation bounds. Okay, so Vapnik-Chervonenkis bounds for balls. So let's say we're in Euclidean space of d dimensions. Okay, what VC bounds tell us is that in our d-dimensional space, okay, or in this room is a three-dimensional space, if you look at any ball in the space, there are infinitely many balls, of course. Look at any ball of any radius. That ball, if you will contain roughly the expected number of points, okay, plus or minus some error bar. But the error bar is very small, okay? And so, okay, and so the remarkable thing here is that this holds uniformly over all the balls, even though there are infinitely many of them. Okay? The key thing is what the error bar is. In the case of these balls, the error bar is about d log n. Okay? So if you have n points, each ball will contain the right number of points under the underlying density. Okay? So if the density is f, the expected number of points is the probability mass of the ball times n. Okay, so that's the expected number of points. And the number of points that you will actually observe is that plus or minus d log n. Okay, and this is in the case where, okay, and what that means is that since the error bar is d log n, we really should not look at balls with less than d log n points. Okay, and so that's a reasonable setting for k. So there's no point at looking at just your nearest neighbor. You should look at that's not a significant value. That's not a significant radius. You should look at the radius at which you have at least d log n points, and that's significant. That overwhelms sampling error. Okay? So that's the first thing. Okay, so now let's see why this holds. And I just wanted to give you a quick flavor of the kind of arguments that arise over here. So we have these two weird clusters, okay, and we're turning this knob, and all we need to say is that these graphs, and whenever the knob reaches some value, certain points are active, okay, and as the knob keeps turning, more and more points become active, and at each setting of the knob, you put some edges, okay, and we just have to argue that there's some point at which all the points here are active and connected, all the points here are active and connected, and there's no way to get from here to there, okay? And that means that these points will lie in disjoint subtrees. Okay? So because of these density bounds, because this is higher density and this is higher density and that's lower density, it's very easy to argue that there is some point at which everything here is active. Because of these VC bounds, these radii r of xi, the distance to its kth nearest neighbor, is really very significant. Okay? And so there really is some point at which all of the points in here are active, and all of the points in here are active, and none of the points in here are active. And that means that at that point, there's no way to get from here to there. Okay, so they are separated. The hard part is to show that at that point, these are actually connected. Okay? And so in these kind of analyses of these processes, it's connectivity that usually is troublesome. Okay? So there's certainly a point at which all of the data points in here are active, all of these are active, and none of these are active. So they're separated, and we just have to show that they're connected. Okay? And so this is the situation we're looking at. We have a single cluster. Every point in the cluster is active, and we just have to show that they're connected, that there is enough points in here that they're all a distance r from each other. Okay? That you can get from any one to the other. Now, this is kind of a bad case because there's this narrow bridge in here. Okay? So what's the worst case? That's the worst case. Okay? Where the whole thing is just one narrow bridge. And you have one data point at this end, and you have one data point at that end, and you have to show that these are connected. Okay? So you have to show that there must be a point here and there and there and there, you know, something like that. So there really is a way to get from one to the other. And that's where that alpha comes in. Okay? That's why it's not, that's why we end up, the larger we make alpha, the more edges we have in here, and the easier it is to show connectivity. And so we use alpha equals square root 2, and it would be really nice if somebody could show that you could just use alpha equal to 1. Okay, that would completely remove, you know, but I have no idea whether or not that's true. Okay, and so I'm not going to go through the argument. So the argument is a little bit subtle, but basically you construct a path from one to the other to show that within each cluster things are fully connected. Okay, and the open problem is whether alpha equals 1 works. Okay, so one of the things I wanted to mention is that, you know, so I said that there is a lower bound where you can show that, you know, so I said that, you know, for any given cluster, you need a certain number of samples for that cluster to be detected. Okay, and then I said that, you know, there's a lower bound showing that you can't do much better. And I'm not going to actually tell you the lower bound. I'm just going to tell you the inequality on which it's based, because this is such a nice and powerful inequality. Okay, this is called Fano's inequality, and it's just a tool in information theory. And you know, it's really worth knowing, because once you have a handle on this, you will, you know, you'll just be able to apply it to so many different statistical estimation problems. Okay. And so let me just tell you what this is. And you know, this is what we use, and I won't go into how exactly we use it. Okay? So Fano's inequality is presented as a game between a player and nature. Okay? So you have nature and you have a player, and before the game begins, they agree on a predefined set of distributions, theta 1 to theta L. Okay? So nature and the player have agreed on these distributions, and then the game begins. Nature picks one of those distributions, but doesn't reveal which one it's picked. Okay? The player has to guess. Okay? So the player doesn't know, but what the player gets to see is n IID samples from that distribution. Okay? So nature and the player, they've agreed, these are the distributions we're talking about. Nature picks one of them, doesn't say which it is, and the player gets n samples from that distribution. So here's what Fano's inequality says. Fano's inequality says that in order for the player to get the right answer with probability at least a half, okay, the number of samples it must see is at least this much. It's log the number of distributions divided by 2 times beta, and beta is the average KL divergence between the distributions. So if these distributions are really far apart, if those L distributions are totally different from each other, it doesn't need to see a lot of samples. But if the distributions are really very similar to each other, then it needs to see a whole lot of samples. Okay, so this is Fano's inequality, and it's just one of those things that is really useful and nice. Okay, and this is what can be used directly to show a lower bound for this problem. Okay. So let me talk about what some of the more recent work on this question has been. So the stuff I've told you about was from a few years ago. And what was shown recently is by Pertuffe and von Luxburg, is that in fact you can also use a nearest neighbor graph for this. Okay, so you can construct a much sparser graph where you never connect each point to more than its k nearest neighbors. Okay, in the graphs I talked about, when the knob gets really far along, there's going to be a lot of edges in there. Okay, and what they show is that you never need to connect each point to more than its k nearest neighbors. Okay, so exactly the same procedure, but never go further than the k nearest neighbors. And then they show that you get a similar consistency result. Okay, and the open problem over here is to come up with other simple estimators. So currently, these are the only two algorithms that are known that converge to the cluster tree, and it's very likely that there's a much larger family of procedures. Okay. Another problem, another interesting issue over here, is that I was talking about this notion of consistency, and this is something that Hartigan came up with in the 1970s, and it's really nice. I mean, it's subtle and it really captured a lot. But now that we've handled this, we can ask for stronger notions of consistency. So what Hartigan says is that if you have two clusters, you want them to end up in disjoint subtrees. Okay, reasonable. But what that allows is it allows you to also overly fragment the data. Okay, so it's just telling you that different things have to stay apart. But it allows you to have excessive fragmentation, and I'll show you what that means. Okay, so when you have a density like this is the kind of cluster tree you hope for. By the way, this is what a cluster tree looks like. Okay, it's like an inverted hierarchical clustering. We're used to seeing hierarchical clusterings the other way around. Okay, so I mean, when you run something like single linkage or complete linkage, you know, you have the top of the hierarchy, which is the whole data set, and then you split it into 2 clusters and 3 clusters. And we normally focus just on the top, right? And then, you know, as things get further, we you know, our eyes glaze over and we don't look at the rest of the hierarchy. Cluster trees are the opposite. You have to think of them, you know, upside down. And the most significant parts are these, because these are the high density regions. This is where the information is sound. If there are low density areas of the space, frankly, you have no idea what's going on over there. Okay? The part of the space that you can really be confident about are the high density parts of the space. So it's really kind of opposite to, you know, how we normally see hierarchical clustering. But anyway, for a density like this is the kind of tree. Let's say you sampled 4 points, 1, 2, 3, 4 from the left, and 4 points, 5, 6, 7, 8 from the right. We'd want something like this, you know, where there's just a single fork and then you gradually get narrower. But a fragmented version like this is also permitted by Hartigan's definition. And this is a problem that has been studied a lot in the context of cluster trees in the statistics community. And so recently there's been some nice work on that. In fact, most recently by Belkin and Wong. Okay, so stronger notions of consistency. Anyway, so some more open problems. You know, so for a hierarchical clustering algorithm, we want these clusterings to converge to something meaningful about the underlying density, right? And this notion, I think, you know, meets that requirement. It's something that makes sense. And I would love to find any other notion. Okay, I don't know of any other that seems reasonable. Okay, and I think that would be really interesting if somebody could come up with a limit, you know, a limiting clustering that you know, is sensible. Okay, so this is an example of a sensible one. There has to be some other. I don't know what they are. Okay, and the second open problem is that this is really just for densities. And what happens in discrete distributions? Is there something similar one can do? Okay, so that's all I was going to say. So, are there any questions?
So, while you mentioned the initial k-means clustering, so what is the practical challenges you're facing in the identification of the k? And second challenge is, how do you validate the clusters?
Yeah, so I think one of the issues with k-means is that k-means is the algorithm of choice for vector quantization, where you have a large space and you just want to divvy up this, you just want to cover the space uniformly, with points, so that the loss, the distance from each point to its representative, is not too large. Okay, k-means is absolutely the right thing to do in that case, and it is used in that context, for in audio coding, for example. But if you're actually looking for natural clusters in the data, then there's no reason why, the k-means cost function would recover one of those. So yeah.
Let's say a clustering. How do you define that? How many clusters you need?
Well, yes, you get back this tree, and then you just have to look at it and try and decide, what suits you. You just gotta.
Optimum number of clusters.
No, it doesn't. There's no way to really answer that question. I mean, there's, yeah. Yeah.
So isn't this, so you showed that you need to have a minimum density, right? That d log n thing that you need, after which there is no statistical guarantees that the clusters are good.
Well, the d log n thing says that, so this business of looking, let's say you have a data point and you say, what is the distance to the nearest neighbor, okay? And you ask, is that a significant number, okay? That's hard to argue because that distance has got a high, it's got some expected value, but it's got a high error bar on it. But if you say, what is the distance to the d log nth nearest neighbor, that's much more significant. So it's got an expected value, but the error bar on that is much smaller. Okay, so that's the issue, So in all of these things, we're looking at the distance from a point to some neighbor, and how far does one have to look before that distance is close to its expected value? It has a nice concentration property. Yeah. When they're sparse. So there are two things. So the first thing is that the thing I've shown is only in continuous spaces. Okay, so I mean, there's only densities. So if these are sparse vectors, then what that means is that they're just unions of these sort of lower dimensional. It's just a mixture of very low dimensional densities. So you would just apply the low dimensional result. I think it would be interesting to get a result for. So one thing that has been shown is that if the data lies on a low dimensional manifold, then then the dimension that you need in here, the d, is the dimension of the manifold and not the dimension of the ambient space. And that was shown recently. State of the art. I mean, so the thing is that all of this work. I mean, so this is this would be the one in any dimension, but this has not yet reached the point where it is practical. And the reason for that, I mean, so we've run it and it does nice things and so on. But the reason for that is that like single link, this is just like single linkage, and like single linkage, it is n squared. And quadratic is like the new exponential. So it's so we're looking at ways to really speed that up, and that's what's needed to really make it practical.
Great. If there are no more questions, then I'd like to ask Pradeep to come and thank Sanjay for his time to come and teach us here.
Thanks a lot, Sanjay, for amazing lectures, and thanks for flying all the way from San Diego.
Oh, thank you very much.